Professor Dave and Chegg here. We have been relating the new parameter of Gibbs free energy to a variety of other concepts. So let's examine one more such relationship. How does delta G relate to the work done on or by a system? Let's look at this as well.
As we know, the sign on the change in free energy for a particular process tells us about its spontaneity. Negative means spontaneous. Positive means non-spontaneous, but the change in free energy also tells us how much work can be done by a particular process. In fact, the maximum possible useful work that is obtainable from a process at constant temperature and pressure is equal to the change in free energy for that process, such that W max equals delta G. This is why we call it free energy, because it is the energy available to do work if the process is spontaneous. Conversely, when a process is non-spontaneous, delta G tells us the amount of work that must be done on a system to get the process to occur. However, the amount of work we actually obtain from a spontaneous process is always some fraction of the maximum possible amount. It is physically impossible to utilize 100% of the free energy produced by a spontaneous process. This is because some energy is always lost, most often due to heat. Look at this diagram of an alternator which charges a battery, which then discharges to the starter motor. As the current flows through the wires, some of the energy is lost as heat emanates from the wires. The greater the current, the more heat that is lost. This can be minimized by utilizing a low current or using better insulating materials, but ultimately the only situation that would involve zero heat loss would be zero current. Any process by which we try to harvest energy to do work will inevitably result in some portion of that energy being wasted. Only a hypothetical pathway would be 100% efficient, resulting in what we can call a reversible process. But this is not actually achievable. All real processes are irreversible. We can't run something forwards and then backwards and retain the energy we started with. Some of the energy will be lost to the surroundings, usually in the form of heat. This is actually another way of expressing the second law of thermodynamics, in line with the version describing the inevitable energy loss of any heat engine.
The best way to summarize this is as follows. As we use energy, we degrade its usefulness. This scientific fact has relatively profound philosophical ramifications, particularly for a society such as ours, which depends on energy production. Rapid consumption of fossil fuels is untenable even from the standpoint of thermodynamics, so this issue should be a primary focus for the human race as the 21st century progresses. Professor Dave for Chegg. See you next time.